picking up where we left off, we just defined a Noetherian ring, which I'll go back and put the definition up for you one more time. This is a commutative ring in which every strictly ascending chain of ideals eventually terminates. That's a Noetherian ring. And of course, the integers are Noetherian because the integers are everything you'd ever want them to be except maybe a field. But what I'd like to do is just discuss with the integers being Noetherian how this plays into our proof in terms of, we've seen the fundamental theorem of arithmetic, but what does this mean in terms of ideals? Suppose that we started with a composite integer. Let's take, for example, 100. Now that happens to be a non-zero non-unit, so we could take A and we could write it as B1 times A1 as 25 times 4. So let's have 25 be the B1 and 4 be the A1. So the ideal generated by 100, which is multiples of 100 in the integer, are certainly multiples of 4. And in fact, this is a strict containment. There are more multiples of 4 than there are multiples of 100. Now 4 is not irreducible, so we would take 4 and we would write it as B1A1 as 2 times 2. Now 2 happens to be irreducible, so our chain here, the chain of A contained in A1, contained in A2, contained in so on and so forth, is 100. The ideal generated by 100 is contained in the ideal generated by 4, is contained in the ideal generated by 2, and this is where that chain would terminate and we'd have our irreducible element, which is 2. Notice that this is, strict subset, and this ideal containment corresponds to the idea that we start with a large number and we break it up as a product of smaller numbers, and we can continue breaking up smaller numbers into smaller numbers until eventually we get irreducibles. Now, the next thing that I want to say is that where does this concept of something being a Noetherian ring, where does this lie in terms of its relationship with all the other things we've been throwing around? Where does this fall with respect to PIDs, UFDs, and Euclidean domains? And one thing that you can show is that all PIDs are Noetherian. Now, however, when you break it down from a PID and you say, how about with a UFD, the concepts of a UFD and a Noetherian domain are independent, which means that there are Noetherian domains that are not unique factorization domains, and there are unique factorization domains that are not Noetherian domains. And these are somewhat difficult to come up with examples for, and a little bit beyond what we want to be doing right now. Well, they're not all difficult to come up with examples for, but this is not something that we really want to concentrate on, because Noetherian domains are somewhat of a side note that I think are really cool, so we're not going to go too in-depth into this concept, but it's just I wanted you to be aware of where the concept of Noetherian lies with respect to all the other concepts we're introducing in these slides. Now let's return to this sketch of this existence proof that PIDs are UFDs. So what did we do? We started out with a non-zero non-units, and we wanted to break it down, and the first thing we really wanted to argue was that any non-zero non-unit has an irreducible factor. And the way that we did that is we used the Noetherian condition to argue that eventually this sequence of A sub i's terminate, in which case we had an irreducible element. So what that meant is after a finite number of steps, let's say after n steps, we had taken A and we had written it as B1 times B2 all the way out through B sub n, and then we had multiplied that by A sub n, and we stopped at an A sub n where A sub n was irreducible. Now to continue with this proof, what we want to finish sketching is just the proof that every non-zero non-unit has a decomposition as a product of irreducibles. We're not going to talk quite as much about the uniqueness of this up to rearrangement of terms and up to multiplication by units. But let's say all of these numbers in the beginning, this B1 out through Bn, or I shouldn't say numbers, I should say elements, the B1 out through Bn, let's just call them C1. Let's abbreviate that and make it a little bit shorter. If C1 is not irreducible or a unit, right? If C1 is irreducible or a unit, then we're pretty happy. A is written as a product of irreducibles. If it's not, let's rewrite it. Let's rewrite it as C1 is C2 times P, where P happens to be irreducible, and we can do that because we've just argued that any non-zero non-unit has an irreducible factor. So here's another element, B1 multiplied all the way out through Bn. It's a non-zero non-unit. So let's write it as an irreducible element times something else. And then what we're going to do is a really similar argument to what we did before. We're going to again use the Noetherian condition to argue that the C sub i's eventually become units or irreducibles. So we started out, we got one irreducible factor, that's the A sub n, and with everything else that was left over, we then just keep decomposing that is products of irreducibles in units. And we know that we can, every time we take something and we want to break it down and make it smaller, we argue that this process is going to eventually stop using the Noetherian condition. The end of the proof, that gets us that we can take an element and write it as a product of irreducibles. The thing that we're going to do next is we're going to show that this factorization is unique up to multiplication by units and the order of the multiplication. That uses an inductive argument, and I generally find inductive arguments at this stage of our life kind of boring, but the interesting part of this argument uses this fact that in a PID, the concept of being an irreducible element and being a prime element are the same. And that's really the interesting part of that proof, and so that's what I'd like to focus on going further. This is just noting that, again, the whole structure of this entire proof is extremely similar to the proof of the fundamental theorem of arithmetic, and this similarity is even more noticeable when you're proving uniqueness of this factorization than it is when you're proving existence of this factorization. So let's go back and let's just reconcile this. This was something that I mentioned right at the beginning, that in general the concepts of prime and irreducible are not the same, and we started out by giving an example of a domain where we could have irreducible elements that were not prime. However, prime always implies irreducible. What we want to show is that if we make the stronger assumption that we're working inside a PID, that the concepts of irreducible and prime line up, and they're really the same. So to prove this, let's suppose that P is an irreducible element of a PID R, and then let's show that this is prime. So we want to assume that P divides the product of two elements A and B, and what we want to prove is that either P divides A or P divides B. Part of the reason I'm including the proof of this lemma in our slides is that my proof does differ from the proof that's in your book, and I'm a little biased, but I like this proof a little better, so let's go through it. What we want to show is that either P divides A or P divides B to show that this irreducible element happens to be prime as well. So let's create an ideal. Let's let I be the set of elements in our PID that have the property that A times R belong to the ideal generated by P. So what I am going to leave as an exercise, because it's a really straightforward application of the standard sort of three-step ideal test, you need to show that I is in fact an ideal of this domain R, and that I'm going to leave as an exercise to you because that's extremely straightforward. But what I want to note is that this ideal that we've created is kind of special. It contains two very nice elements. In particular, the element B belongs to I because A times B is divisible by P, which means it belongs to the ideal generated by P. And it also happens to be the case that P belongs to the ideal I. That's because if I look at A times P, that definitely belongs to the ideal generated by P. It's very clearly a multiple of P. Now here I want to use the fact that what I'm working with, this domain, happens to be a principal ideal domain. So I want to take this thing that's I, we've now shown via our exercise that it's an ideal, and we can write it as the ideal generated by some element C. Since we've noted that P belongs to this ideal I, it follows that we can write P as a multiple of C. That's what it means for P to belong to I and for I to be the ideal generated by C. So P is equal to C times S for some S in our domain R. Now we have to finally use the fact that P is irreducible. Because P is irreducible, we know that one or the other, either the C or the S, has to be a unit. In the first case, if C happens to be a unit, then I is the ideal generated by a unit. That means that I is the entire ring. In particular, 1, our unity, belongs to I, and that means that 1 times A belongs to the ideal generated by P, and we conclude from this that P divides A. So that's the first situation, if C is a unit. In the other situation, if S happens to be a unit, then I, this ideal, is the ideal generated by P. The ideal generated by C is the same as the ideal generated by P when P and C are off by multiplication by a unit. In this situation, we've noted again that B belongs to I, and I is the ideal generated by P, which means that B can be written as a multiple of P, and P divides B.